Yeah, thank you very much, and thank you very much also for the patience, my slow responding. So a lot of things were going on last month. So I would like also to thank the organizers for giving me the opportunity to stop here. So it's always a pleasure being within the community, the Money Away community. So my talk is going to be a little bit different. So some of you might think that it's kind of trivial, but I think it has some possible impact also investigating silicon gas. My background is actually in applied mathematics, but I've been working here in the department for more than a decade now, and I'm interested in wave physics. So it's somehow a bit complicated, and now Akhmediev keeps telling me that I'm also delocalized, so not really localized on location, so it makes things a little bit exciting, but also sometimes difficult. So the work I'm going to present is in collaboration with Yu Chen He. So he's now postdoc, my former PhD student at the University of Sydney, and he's currently in Hong Kong. Short advert. So even though this book was more targeting graduate students in physical oceanography and ocean engineering, but mathematics, of course, fundamental language of all applied scientists. So some collection of chapters, some of them at least, you might find interesting and maybe worth having a look. So the topic of rogue waves, of course, of significant importance for ocean engineers. For different reasons, of course, because these rogue waves impact ships and marine structures, etc. And the oceanographers define extreme wave to be a rogue wave if its height exceeds twice the significant wave height. The significant wave height is defined for Gaussian C to be 4 times the standard deviation. There's also another notation, basically, where they define the rogue wave as a function of the maximal crest height, and the crest height should exceed 1.2 times significant wave height. So just maybe a warm-up for the lab tours, and I think they have a similar facility here as well. So why they're interested in the topic of rogue waves, why they're interested in modeling rogue waves properly? Well, one of the experiments, and it's a classical thing, what they do and what we did in Sydney here. So they place basically a monopile or a cylinder, and then they generate basically boundary conditions, and they want to have an extreme wave forming there to check the reliability of the structure. So, apologies. This is an example of what we did, for instance, when using nonlinear models, in this case, a Peregrine solution. So we generate basically the maximum peak at that location, and that's why these solutions are valuable, because they are defined in time and space, so we can define the boundary conditions accordingly to have that extreme wave forming exactly at that location. So for that respect, it's very valuable. And you can see, if you look at the corresponding forces, so here we keep increasing the steepness of the carrier wave. If you look at the forces here, the response is linear, but at some point you start having this kind of non-transient response of the structure. We call ringing response of the structure, and it's because basically with the increase of the spectrum, because of the wave focusing, you can trigger basically the eigenmode of the structure, and you have to avoid this to happen, of course. So this is just an example. So this is very technical, of course, and I'm going to spare you details on this. Coming to the rogue wave modeling, of course, is a famous, my apologies in German, but I like this picture quite a lot. So the first principle, where I just explain the rogue waves from the wave dynamics only, is the dispersive focusing. You have long waves travel faster than short waves, and then you have the unfortunate circumstance, you have this wave focusing here, which is quite trivial. What I like more is the so-called modulation instability, and this is actually the solution of Dimitri of the Peregrine breather on a denoted wave, which I find quite nice and suitable when you describe this problem. But I would like to add a slide actually to his talk, which is something which people actually, you're more familiar with that, but I'm not sure if everyone is familiar with this degenerate solitone solution. So this is quite interesting because you can construct these. Apologies. You can construct these actually as a superposition of different envelope solitones. So if you use you choose 2 solitones with 0 speed, different amplitudes, you can have them pulsating here. You can get the Satsuma-Yajima breather, second-order solitone solutions. The amplitudes are 1.5 and 0.5. But then if you choose basically the same amplitude and same velocity, you get this kind of degenerate case, which is could be seen as a mathematical artifact, right? What is a degenerate case? Is it physical? And interestingly, you can get this solution also if you look at the solutions which are described by Dimitri and his co-author Shen, I think, as far as I remember. So it's a family of solutions, and based on the DN background, we know that one limiting case of the DN background is a regular wave-train solution. So then we get the Peregrine solution, and now if we move to the other case where we move to the other opposite soliton limit, we get this degenerate solution as well. So that's why I like calling this a Peregrine soliton on zero background. And it's interesting. That's also. Yes.
What is the degenerate?
So basically, you collide the solitons and they collide, and then they don't meet each other. Yeah.
So that why you
Oh yeah, of course, yes. And you can get this from the solution as well, which is quite interesting. And it's physical, it can be observed, and all these solutions have been observed as well, as Dimitri mentioned earlier. Now, interestingly, there's a lot of debate in the community. Is modulation stability or nonlinear wave groups a topic for extreme waves? And there's more and more evidence of this. In fact, there's a recent paper published in Journal of Physical Oceanography where they showed that a sea state with strong wind speeds exhibits wave groups which have the feature of nonlinear wave group dynamics that's written here. There are much more evidence, but I don't have time to discuss it here. Happy to chat about it later if there's an interest. So modulation stability, what is it? I think we discussed this, or this has been discussed many times this week. So this has been already shown by Katie and Pavel. I'm going to skip this. But basically, if you look at the linear problem, so we know that the cosine function is the solution of the linear Roswell problem. Now, if we look at the problem second order in steepness, Stokes correct this to the second order here. So we have introduction of the second phase here. And the waves basically becomes more and more toroidal, right? So they're not pure cosine waves, but rather toroidal waves. And Benjamin Fair, they showed basically for giving wave steepness here. So AK is a wave steepness is a crucial parameter which controls the nonlinearity of our water waves. So for giving wave steepness, omega can be found using dispersion relations. So that's a critical point here. So there's a range of unstable frequencies for which the waves will start to grow. The sidebands will start to grow exponentially, right? This is the gain curve, which has been shown by Katie. And what happens basically here is like when you trigger sidebands, these will start to grow exponentially. And with the broadening of the spectrum, we start having focusing of the wave field in a parallel manner, as you can see here. And that's basically modulation stability, classical sense. So basically, it's the amplitude modulation of your wave field, which then will start to grow exponentially. And this has been shown also qualitatively in experiments done by Benjamin afterward, in the same year actually, where they started with a regular Stokes wave train, and after a propagation distance 60 meters from the wave maker, start observing distortions of the wave field. However, so even though, of course, this is a kind of fundamental mechanism, but modulation stability, or based on the linear stability analysis of the second order Stokes waves, in a sense, it's not physical because it just tells us that the sidebands will start to grow exponentially. That's it, but nothing grows to infinity, right? So we need saturation. Saturation will be reached at some point, and it's not described by the linear stability analysis. And another, in fact, these are experiments which show that clearly. So these experiments by Tule and Ozera back in '99, they start basically from a three-wave system. So the main carrier frequency here to sidebands, and then you have a transfer of energy from the main frequency to the sidebands. You have this sideband cascade, but then you return again basically to your three-wave system. So this referred to the Fermi-Pascal recurrence for deep water waves. And again, reach saturation, which is not described by the linear stability analysis. This can be done, though, when we move to the Schrödinger equation. I love this equation, actually. I wanted to move from it years ago, but I always come back to it because there's always something nice to be explored there. And it's mathematically very interesting. My apologies to be upside here. You can see it now. It's mathematically very interesting, but also it's rich in physics, which is unbelievable, actually. And we keep exploring new things, and anyway, and also making bridges between disciplines. So it's an unbelievable equation, actually. This is an expression in finite depth. Yeah. So it's not so here we evolve in space, as Panos mentioned. The optics people and hydrodynamic people like to measure time series evolving in space. So we have this kind of time-like representation, as we say. And it can be constructed for deep water waves, but also in finite water depth. And the parameters here, alpha and beta, are very complex and depth dependent here, and are, well, ugly, but we can deal with them in an easy manner, of course. So this has been shown for the first time by Hashimoto and Ono back in '72. The origin, however, is from the deep water waves. So deep water wave things simplify. So when the dimensionless depths go to infinity, the Hopological tangent will tend to 1. The dispersion relation simplifies, the group velocity also, which is half the phase speed. And then we end up with these famous deep water nonlinear Schrödinger equation. If you invert x and t, you end up with this expression here, which has been found by Zakharov as a special case of a Zakharov equation for a narrowband process. Thanks, Pavel, again, for letting me know that it was already published in '66. So now I'm going to use 66, 67, where it has been published actually in JETP, the Russian version. So it came to us only a year later in 1968.
The A didn't see here.
Yeah, apologies. Yes, I don't know what happened. Most it's all the A's are upsides, my size. Apologies. Here's 2, right? So most probably transferred this here. So yes, side, of course, yeah. So interestingly, if you scale this, and there you see also simplicity from a mathematical point of view, you end up with a scaled form of the Schrödinger equation, and we all know that's integrable, and you can find some fancy solutions. Some of them are physical, some aren't. But interestingly, because of this integrability, as Dimitri mentioned, you can use them as a trigger, right? To trigger experiments to understand what's happening in the real world, because the real world is not integrable. So whatever experiment we do in optics or water waves or Bose-Einstein condensation, we're not dealing with an integrable system. I mean, even Navier-Stokes is an approximation. Everything is an approximation, right? So, but if an approximation works well and captures most of the dynamics, that's quite valuable. And so basically, for the hydrodynamic Schrödinger equation, so if the dimensions depth is above 1.363, we deal with that with bright structures. So this is called this envelope soliton. And in water waves, so these are is the envelope. So the waves actually lie underneath, right? So the carrier wave is has much faster oscillations, and this is just the envelope which we don't see. In the optical experiments, oscillations are so fast that actually we see and can measure directly the wave envelope, which we can't. But I'm going to show you later how there are some straightforward tricks how to do that. And interestingly, if you look at the defocusing case, so when the dimensions depth is smaller than 1.363, we have the so-called dark solitons. Actually, Dimitri mentioned this already. Now, back to modulation stability. This is the famous Akhmediev breather solution, which has been found by Akhmediev and co-authors in 1985, and can be also derived from the Kuznetsov-Ma breather as well. So this interesting fact about this solution, it's basically we call it a nonlinear stage of modulation stability, because it not only describes the initial three-wave system initialization, if you wish. So you reach the peak frequency, the peak of amplification here, which translates to severe broadening of the spectrum and this infinite number of sidebands which appear here, which you also can describe analytically. And then you come back again, basically, to your initial three-wave system. And this solution is again analytic, and you can actually modify the parameter B here to modify the modulation frequency or modulation period of your wave envelope. Now, why are we interested in doing experiments? It's not only for model validation to understand if it's an artifact or something interesting, but we learn something new. Just a quick slide here on one experiment we did back in Taiwan, together with my colleague Olivier Kimun. Olivier Kimun, who unfortunately passed away recently. So we basically tried to observe Akhmediev breather. So here we have discretized, basically discretized resolution in propagation direction. That's why you see the peaks here. We can actually smooth them out nicely, but we didn't want to do it that time. And we were intrigued, actually, why do you have this kind of phase shifted recurrence, which is not supposed to happen if you run your numerical simulation. So what we, after discussions with people in optics, we realized actually that we always have an exponential decay of your wave field, which you're able to capture actually in our wave tank. And by adjusting the Schrödinger equation here, this dimension is units here, but of course we did dimensional units. we got something very similar. And this is something new, actually, which came up at that time. And nowadays we can use this or analyze this quite rigorously with a finite gap theory, etc. All right. Now, this is the Peregrine solution, which is famous because the case of infinite modulation period or zero modulation frequency. And what looks to be very trivial or very straightforward to obtain is actually not so if you think about it from a physical point of view, because this is a case of infinite modulation period. What is infinite? Is it physical? And in fact, as I'm going to show later, if you truncate this properly, you still can observe the Peregrine dynamics, in fact, not only one medium, but in several. And this is interestingly one of the, maybe now the most cited paper of Peregrine, even though he did actually a lot of great fundamental contributions in wave hydrodynamics, but this is now becoming number one. All right, so to the experiments, and maybe another warm up to what to expect. If you have time, we can program in the Peregrine in the labs later to move the paddle accordingly. So it's quite simple, actually, because if you have an exact expression, dimensional expression of our breather or soliton or any localized solution of the Schrödinger equation, we know that at first order of approximation, we can basically define the carrier wave. We just multiply this by the surface elevation, sorry. So we multiply the envelope by the carrier wave and we just take the real part. And now, because we're generating time series, we just have to fix basically the spatial coordinate at the position of interest. So in our case, we want to observe the breather here 10 meters after. So we just fix this to be -10 because we start 10 minutes earlier. And so, but we should not forget actually that with the exact breather solution, we have not only the information of the amplitude modulation, but also phase, which is of course trivial, but this has some implications. At least we have not looked at this in the context of ocean waves, I'm going to show later. Now, interestingly, if you have a time series, let's say measured by the wave gauge here, how can you measure or find the envelope? So first thing, what we can do in a straightforward way, we just apply the Hilbert transform and get the imaginary part. And basically the phase, nothing else than this trivial geometrical construction, which we all know. And therefore, if you have the time series, you can also collect the phase out of the wave field in the experiment. All right, so this is how it looks like for water wave in the water wave tank. So all these measurements here have been aligned by the value of the group velocity. So we have them nicely aligned here. So these are the experiments, and this is theory. It's not perfect. Again, it's not. Again, it's just the Schrödinger equation is just an approximation to third order of the Euler equations, but it's quite nice. So it captures most of the dynamics, at least, of this extreme wave. And again, the Schrödinger equation is supposed to be a simplification of the Kharov equation for a narrow band process, right? But however, if you have focusing here, you have a broadband, you have a spectrum broadening. And so a lot of people actually did not want to touch this solution because they thought it's not physical. And in fact, again, the Schrödinger equation works actually much better than initially thought. So I'm not going to mention these carrier wave and wave steepness here. So usually we're all around 1 centimeter, 2 centimeters, and a steepness of 0.1 to avoid wave breaking. So we slightly vary these numbers, but they will be around this range. Okay, so I'm going to skip these details because I want to focus more on the proof of concept. So, and the whole story actually started with this famous paper by the group in Dijon and Franche-Comté, where they observed the Peregrine breather in optical fibers. At that time, they were not able to generate exactly the case of zero modulation frequency or infinite modulation period. So they started with the main frequency peak and only with one sideband because they were able only to inject two wave systems in a sense. And then they took this sideband very close basically to the case of the Peregrine, but not really, but they were very close, of course, right? Nowadays, of course, they adjusted the apparatus and it's straightforward to observe. Now, however, this kind of triggering modulation stability from a one sideband only was quite interesting. So all these are experiments here. So we have a nice spatial resolution here because we have different wave gauges we place around along the wave maker. So we can see from the spectral domain here, we started here from the two sidebands, like the classical symmetric problem. And now if you start only with one sideband on the left side or the right-hand side, you can still trigger modulation stability, which is in a sense trivial because the full-wave interactions tells us that you have this kind of symmetric energy transfer between the carrier to the sidebands. However, if you look at the longer propagation distance, so this is all simulations here, NNS simulations. We did also other simulations, but yeah, that's not the main topic of the talk. But we can clearly see here you have the perfect recurrence. If you start from the symmetric boundary conditions, however, because of this delay and asymmetry, you get some additional speed in these FPU diagram. All right. Just parenthesis, going back now to the observations. So after the Peregrine breather, which has been observed in optics, there's another observation here in plasma. And I want to mention this recent paper, actually, which has been published by Panos and his co-authors, which is quite remarkable because, and maybe I would like to congratulate you and your team for that, because it's not easy, basically, to handle both let's say atoms in focusing regime. So Bose-Einstein condensates are more, I would say, prone to be used or to observe these solutions, dark soliton solutions. But once you have you come to the defocusing regime, you have explosions, etc. So it's very tough to handle. So this is very nice work, which appeared actually recently and made it on the cover of Peregrine. All right, so now we know how we generate these solutions in a tank and what's valuable to think of when we generate these solutions. But I'd like to come back to this paper, which has been published basically in 2020, but the experiments have been conducted back 2015. So at that time, we were interested in looking at the evolution of dark solitons or Peregrine breathers if we just suppress the phase, right? And the phase can be easily suppressed if you go back to the boundary conditions here. So if we just basically start our evolution with the absolute value of the wave envelope, we suppress the phase and we just deal with the amplitude perturbation, that's it. And the question is what's going to happen afterwards? So again, it seems trivial, but it has implications. So we started basically, this is a observation of a Peregrine breather over 70 meters of propagation. So the tank length here was 90 meters. Same story, start with small perturbation, focuses, defocuses, and then this is the corresponding numerical simulations. Actually, you can also use analytical expression, of course, because we have one, right? The boundary conditions is as the following. Now, if we start basically with the same boundary condition, but we take the absolute value, so we suppress the phases. So we see that we get the same focusing actually locally, right? And then you start having this initialization of this cascade. Actually, Gino was talking about yesterday. Also, Tamara worked on this actually quite a lot as well. You start the initialization of this kind of cascade, which happens, and locally, is it a Peregrine breather or not? So in terms of amplitude, we reach that focusing, and it's quite in agreement with what we observe in the tank. But is it a Peregrine breather or not? Well, we have to look at the phases, right? So this is basically the phase evolution. This is from the first time series, basically the first time series we measure after the 5 meters of propagation here, right? If you look at the phase, we get basically the start of this phase shift, which starts to move up to 2 pi at the maximum location. And if you look at the analogous case where we just start with a phase suppressed initial condition, we still get that phase jump. So locally, even though we don't start with the exact initial conditions, but locally we deal with Peregrine breather, right? So which is quite interesting. However, if you look at the dark solitons though, so this is experiments, right? This is not any numerical experiments we performed. So this is experiments just have been allied by the values of the value of the group velocity here. So the dip is here, right? So that's a dark soliton. And again, the waves are oscillating much faster. That's why you see this dip forming. And this is 75 meters of propagation, which is significant. And these guys are quite stable, right? So considering the limitations, again, of our equation, right? So this is what you expect, of course, from simulations. Could have taken also, of course, the solution. But if we start, basically, we suppress the phase here, these dark soliton will evolve into 2 grays plus radiation, right? So, and you can also see it in the experiment. If you look at the phases here, you have a nice phase shift of pi with, when we measure it from the first time series, but also at the end of the propagation, you still have it quite nicely there. But if, of course, you start with the suppressed phases, it messes up the whole picture. So, okay, now we started the evolution by suppressing the phase. Now the question is, what happens if you suppress the amplitude modulation and keep the phase? What is this going to give us? And we did this actually for pure solutions, pure analytic solutions like a Peregrine breather, Akhmediev breathers, etc. And this has been published actually recently, 3 years afterwards. The pictures are the following. So this is, if you look at, this is exact, these are just numerical simulations based on NLS. So here you start with the exact Akhmediev breather, you start having the compression and then the decay again. Now, if you start with a regular wave train, which has the same initial phase, but you start with something regular, but has a frequency modulation, if you wish, according to the solution, you still get a focusing of the breather, but a bit delayed, as in the previous case where you suppress the phase, we keep the amplitude. And you get a recurrence, right? Of course, because it's not the exact solution, and then you start observing the recurrence here. And the same with Peregrine. So if you start with exact solutions, of course, you get this famous picture. But if you start basically from a regular wave train, having this slight initial phase shift, which is described by the solution, of course, as well, you get basically locally again a Peregrine breather. This is a maximum compression point, which is very similar to the exact solution. And then you have this cascade forming afterwards. Now, so these are experiments. These are so the left-hand side will be experiments. The right-hand side will be corresponding numerical simulations of exactly the case where we just suppress the amplitude and we keep the phases. So as you can see here, so this is the case of a pure Akhmediev breather, which is supposed to focus at 12 meters from the propagation distance in the tank. And then this is what you obtain basically when you start just from the pure regular wave train with injected phase. And this is basically the corresponding expectations from the NLS, and the agreement is quite good. And just want to plot basically what we measure after gauge 1. Basically, when you start from a regular wave train, this is what we observe from gauge 1, and then this is what we expect from the breathers. Okay, so it works well for breathers. Now the question is, I'm going to finish quickly, so it works also for Peregrine. So what happens if you have an irregular C state? Apologies, Karim, only 2 or 3 minutes. Thank you. So this is so-called Johnson spectrum, which is a representative C state spectrum, which has been derived by Hasselmann back in '97. So if you start having wind blowing on the surface, you start with ripples. These ripples will start to grow. So in frequency domain, you have a phase shift and increase in amplitude. You get then this fully formed wind C, which can be parameterized as the following, as derived by Hasselmann. If the C outside satisfies this condition, I don't know. It's just a representative spectrum. So we chose these parameters actually for the wave spectrum, which corresponds to very steep waves. And we know the surface elevation can be then derived of this Johnson C state as the following, where phi are random phases, which are randomly distributed between 0 and 2 pi. All right, so we know from the work from Miguel Honorato and co-authors, if you generate such waves, you can look at probability density, probability of exceedance. So the continuous line is the wave distribution. So this corresponds to the case of pure linear waves. However, if you increase the steepness or the degree of nonlinearity, which is here described by the BFI, you start observing a deviation, obviously, from this distribution. And in fact, so this is a condition here for extreme waves. So if you look at this condition, so 1 over 10,000 waves will be rogue based on linear theory. However, if you increase the steepness, you deal with 1 order of magnitude higher here. So 1 over 1,000 waves would be rogue. All right, so we don't have a big tank to do the same experiments, but we can run preliminary numerical simulations, and we look at these extreme events which occur, and we isolate these and do the experiments, right? So this is basically the original one which has been found in the experiments. So all this, so the line here, everything which you see on top is our experiments, and the simulations are on the bottom. So this is the case which we measure. This is what we get from NLS simulations. Now, what we can do, we can construct the wave envelope, suppress the phase, and see what happens. So we see clearly that the amplification is a result of the amplitude modulation. and nothing happens in a frequency if you just suppress basically the amplitude and we start with a phase shift. However, there are cases which are non-negligible where you can get this extreme wave as a result of the frequency modulation, and nothing happens in the amplitude here. So this is quite interesting. You start from a regular wave train with localized phase shifts, and you can have extreme events. It's a kind of nonlinear focusing mechanism in addition to the amplitude modulation one. And there are cases where you have both at play. So we have amplitude modulation and frequency modulation, and you have cases where neither of the two are at play, which actually we found two cases actually which correspond exactly to the 1/10,000 wave, which is a result of a linear superposition. We clearly see that this focusing here is not a result of neither amplitude modulation or frequency modulation. So this is the last slide. We in a qualitative way, we define basically this number R here to distinguish basically which waves occurred as a result of modulation, modulation or frequency modulation. And we found, if you look at the experiments, that most of the cases which bigger than one here are a result of amplitude modulation. However, we still have cases here which should not be neglected, which occurred as a result of the frequency modulation of the wave field. And this maybe could be something interesting, an utilization problem for maybe solid on gas experiments, which we're going to perform as next. And with this masterpiece from Japan, Hokusai's masterpiece, which is now on the new 1,000 yen bill, which just came out recently in July. So happy to take your questions.
I'd like to postpone most of the discussion to the lunch break, but a couple of quick questions.
So, you bring them on the road, please. Never wave break, right?
We have wave break, yes. Of course.
And what's difference for road wave or road break?
Okay. Yes, so if you have a regular wave train, purely regular wave train, the breaking threshold is a steepness of 0.44. This is for Stokes waves. So if you have regular wave train and steepness of 0.44, you start having breaking. So if you start with a wave field and you expect it to have a wave breaking, you have, of course, you have to keep the steepness lower, and usually we keep the steepness of 0.1. You have basically, even for the multi-breaking will be moderate, but there are certain cases we have severe breaking, and of course we have edge dissipation. But in this case, we wanted to basically confirm a proof of concept that we have that this
1,000 road waves is about 0.1.
Oh, I see. Well, yes, of course you can have variations of that, of course. This is based just on linear theory. That's how you do experiments basically to check that curve.
Yeah, no, thank you. So when you show the Peregrine breather, for instance, like you said, that is the power that you plot.
The what?
The power that was on the y-axis. Anyway, I mean, the question is like, do you plot the solution of NLS, so the free surface, like what?
Oh, sorry. Okay, in this case, okay, sorry. So what I showed you earlier was I was plotting surface elevation. Right? Do you see the evolution of surface elevation here? In this case, it's here. For instance, this is experiment. So what we do, we measure at so we have a propagation distance of 25 meters, but we have basically 42 measurements. So we can do from each of the 42 measurements, we measure the wave envelope, and then we interpolate, and we get essentially.
When you plot the rope, yeah, I mean, so the Peregrine breather, very early in the beginning.
Yes.
Yeah. So then you had power on the.
This one, right?
No, even earlier, sorry,
Earlier.
it's like a mathematical picture.
Oh, okay. This one.
Yeah.
Yes.
this one.
Yes. This is the absolute value of the solution, right? Just to show you the expected amplitude application, which is on 3.
So that's not the free surface.
No, it's
No,
envelope. It's just the absolute value of the
Yeah.
This is a low.
envelope of the envelope. Yeah, just the envelope. So the waves lie underneath, basically. If this is your initial condition here, so you can imagine this is a small bump here, which you can see in the experiment, which corresponds to, let's say, this case here.
But the free surface reconstruction has more terms, right?
Oh, yeah. Oh, yes. So, yes, this is a good point. Indeed. So what we do, so we just measure, we just define the boundary condition to first order of approximation. But of course, if you measure, you see the second, Stokes wave, third, fourth, etc. You see the whole cascade. But these appear naturally afterwards, so I don't have to deal with it. So if I generate a linear signal, it generates only nonlinear waves shortly after the matrix. So I don't have to deal with nonlinearities. And of course, if I could be more rigorous here, adding second Stokes wave, third, etc., fourth,
Yeah.
can do that, but it does not change much in this curve.
Well, just we have.
Of course, yeah, thank you.